Okay, well, here we go with a new lecture. I noticed by the schedule we're sufficiently far ahead of schedule in lectures that at least some of the lectures for the rest of the semester will only have 3 segments instead of 4. So that'd be about 90 minutes instead of 2 hours. I'm sure you're disappointed. We'll see how that works out. So we'll try 3 segments for this one and for the next few anyway, and see how that works with the schedule. Where we left off was we were just about to do valence bond theory. This is a quantum mechanical approach to bonding. We looked over the Lewis approach to bonding, and the Lewis approach to bonding is nice and simple, but in some ways it's too simple. You knew things had to get more complicated. So the valence bond theory tells us a little bit more about what's going on and why things happen and why they don't happen in some instances. Because just looking at the Lewis models of bonding, the Lewis structures for molecules, it seems like there are a lot of opportunities for bonding between atoms that don't actually occur. And you might wonder why that is. Well, we saw part of the reason with formal charges. Certain arrangements don't work because the formal charges are off. But the valence bond theory gives us a little more in-depth answers as to why certain bonding works out and some doesn't. So the valence bond theory is a simplified quantum mechanics approach. Electrons in orbitals for isolated atoms are in sp or d or f type orbitals. Okay, so electrons are in orbitals localized on atoms, and for isolated atoms, that would be sp, d, or f type orbitals. And by isolated atoms, I just mean atoms that are off by themselves and not actually engaged in bonding. As the atoms approach each other, and with perhaps the potential for forming a bond, as the atoms approach, the charged parts of one atom can begin interacting with the charged parts of the other. You can calculate the energies of interaction for electrons in orbitals at any given distance. And as it turns out, if an interaction lowers the energy of the atom overall, then a bond forms. And if it doesn't, then a bond doesn't form. Or especially if the interaction raises the energy of the system, then you're definitely not going to get a bond. Okay, then you won't get a bond. You can actually look at the energy between two atoms as the distance between the nuclei changes. And so R being the distance between the nuclei and energy being the sort of the potential energy of the two atoms together. And you'll find that as the atoms are far apart from each other, and so I'm going to draw the line going toward the left, because the left would signify small distances, and these are two atoms that are approaching each other from a long distance, which would be out here. So they tend to have basically no interaction until they get within a certain distance of each other. And then the energy starts decreasing for a while, but then if they get too close to each other, the energy goes way up. And it's basically right here that, at the minimum of energy, that the bond forms. So it's the minimum energy of interaction between the two atoms. That's where the bond forms. And at that distance, the orbitals of the valence shell of the two atoms have significant overlap. Because remember, these are distances between the nuclei. The valence shell of electrons is way, way out beyond the nucleus. And so when nuclei get close enough to bond, their valence shells are overlapping with each other. And that's essentially what we mean by covalent bond. They're mingling their valence shells. And the interaction energy at this point is the bond energy. And so in this case, it would be this energy right here. That would be the bond energy, because that, is the minimum energy that the atoms have when they interact with each other. Okay, the interaction energy between atoms is usually negative. And remember, negative energy is stabilizing. Until they get very close to each other. As we saw up here, even at a great distance, the interaction energy between the atoms was slightly negative. And then they reach a certain distance where it's even more negative. And when it reaches its minimum, that's where the bond forms. But if you force them even closer together, it starts rising very quickly and shoots above zero. And so that's a very unfavorable situation. Okay, so that's unless they're very close. And this is especially true, that is that the energy of interaction is negative or stabilizing when atomic orbitals are interacting have a total of 2 electrons that can adopt opposite spins. And this is also known as spin pairing. So they may have, they might both be spin up when they're in the isolated atoms, but if one of them is able to switch to spin down, they can then combine with each other in this new molecular orbital that's forming between the two atoms, and that would allow them to stabilize the situation. Okay. And so this new molecular orbital is formed by the overlap of the atomic orbitals. All right, I don't want to get too far into that because that's a different section that we're really not going to be covering much this session. So that'll be enough said kind of in that direction. Usually what you have is one electron from each atom. Each of them would originally have been in a half-filled orbital. And you have a covalent bond with one electron coming from each atom. So they kind of share them, they contribute equally. I don't want to say they share them equally because that's not necessarily the case, but they contribute equally. Sometimes that doesn't happen though. Sometimes both of those, the electrons in the new bond come from one of the atoms and the other atom doesn't contribute anything. So the orbital that's involved in the bond on the other atom would originally have been empty. Okay, so the empty orbital of the other atom, and that is what's known as a coordinate covalent bond. And that's covered in more detail in a later chapter, so I'm not going to go into a lot of detail on that, except that you now know what it is. And keep in mind that the overlapping orbitals will have an effect on the overall shape of the molecule. So that's for future reference, because basically the outer atoms will be found around the central atom in locations where there are electrons for bonding, because the bond is what holds the outer atoms to the central atom. So you're going to find the outer atoms positioned in locations where the central atom has electrons for bonding. And where the central atom has electrons for bonding is controlled by what orbitals are involved in bonding. And so the orbitals that the central atom has available for bonding will affect the overall shape of the molecule. For a orbital level view, we can look at what happens in water. In water, you have a hydrogen with its 1s electron. and you have another hydrogen with its 1s electron, and then you have oxygen, which has 1s and 2s and 2p electrons. And for oxygen, it's 1s2, 2s2, 2p4, 1, 2, 3, 4. And what you have is these half-filled orbitals, one, the only orbital, and the two hydrogens overlapping with these two half-filled p orbitals in the oxygen, and you get two bonds. Well, actually, it's 4. And so you end up with two bonds. Okay, so we can calculate the bond angles and the lengths and the strengths from valence bond theory. And one other step is hybridization of orbitals. This is also part of valence bond theory. Hybridization of orbitals is important to explain certain geometries of many molecules. There are a lot of molecules whose shapes cannot be explained with the standard s, p, d, and f orbitals. Okay, so there are certain, if you look at the shapes of the s and the p and the d and the f orbitals, and when they overlap, there are certain combinations of overlap that are possible. But even if you look at all of the possible combinations for overlap of those types of orbitals with each other, there's only a certain range of shapes that the molecules would be able to have. And there are a whole lot of molecules out there that have shapes that are not among the list of shapes that would be possible from the overlap of s, p, d, and f orbitals. And an example, a fairly simple example, would be methane, CH4. You have hydrogen with its 1s electron, and you have carbon with its 1s and 2s and 2p orbitals. So it's carbon is 1s2, 2s2, and 2p2. So there's carbon. The theory would lead us to believe that carbon would only form two bonds with hydrogen. Or maybe two bonds and one coordinate covalent bond. And the compound should be CH2. And it should have 90-degree bond angles. Actually, carbon forms 4 bonds with hydrogen, and the formula is CH4. And the bond angles are 109.5. Because as we saw when we did the VSEPR theory, CH4 is tetrahedral. There we go, tetrahedral, like that. And that can only happen if there is what's known as hybridization between s and p orbitals. Hybridization is kind of like a merger. It's like hybridizing animals or plants, where you end up with some characteristics of both. So this can only happen if there's a merger or a hybridization of s and p orbitals. Okay. So the molecular orbitals are not necessarily the same as atomic orbitals. Okay, so shapes of molecular orbitals not always the same as the shapes of atomic orbitals. So hybridization as a definition is a combination of characteristics and shapes of 2 or more standard types of atomic orbitals. And what you end up with would be hybrid orbitals. And these orbitals are still localized on one atom, usually the central atom. But the energies and sizes and shapes are a combination of those of the orbitals from which they are derived. Okay, so the orbitals making them up. And the reason why this happens is because energy density is more concentrated in a given lobe in hybrid orbitals. And this leads to more overlap, which leads to stronger bonds, which leads to lower energy, which leads to greater stability. Hybridization does require energy input. But the amount of energy you get out in stability once the hybridization or once the hybridized orbital forms is usually more than enough to compensate for the energy that you have to put in. Mm-hmm. Okay, so you end up with lower energy overall. Okay, so the central atom is most likely to hybridize, and the outer atoms are usually not hybridized in this case. Okay, so the types of hybridization that are commonly encountered can be identified based on the electron geometry that they're associated with. And so actually, if you can identify the electron geometry of the central atom in a molecule, you know right away what type of hybridization it has. And if you know what type of hybridization it has, you know right away what the electron geometry is. And I see we're almost at 30 minutes, so I'm going to break here, but we'll come back for that in just a moment.